one, if you will, standard deviation of the sampling distribution, otherwise known as the standard error. 68% confidence, we need to go out 2. Now here's, to make it a margin of error for the weights, we essentially have to take 2, I'm going to put 2 in quotes if it's okay with you guys. We know it's not really 2, it's 1.96. But we use 2 because 2's nice, number 1. And we also like 2 because we don't care if it's 1.96 because that machine will do a good job for us. It'll do a good job for us. So we're going to take 2 times the standard error. And the reason I'm calling this a margin of error, we're talking about 95% confidence interval margin of error. 2 standard deviations, boop, boop, gets us out till we include everything except the 5% outliers. And the 2% standard error would then become about, what's that, 0.01 pounds? About 0.01 pounds. Now, we revisit Mike's point. Mike told us the correct thing to do earlier, didn't he? He said, you got to take two, Richard. We got to take 2 of those standard deviations and add and subtract it from X bar. Correct, but we got to use the inferential standard deviation because now we're talking about standing for the entire population, not just standing for our sample. It doesn't end with just our sample anymore. Now it ends with the population. Is that fair? So now let's redo that. Let's redo that to answer the question. The 95. Let's turn this off. What is the 95% confidence interval for the weight of a Del Taco half-pound bean and cheese burrito? How much does one of these things weigh on average? Well, on average, the sample was 0.526, corrected by using the standard error. We have to add and subtract that guy, or the margin, I should say margin of error, because we already doubled it down here, right? So we're going to say it's, and Sue said, what do you use your notation if you don't mind here? What is your notation? It's X bar plus or minus the margin of error, which is how you'll see it in a research type journal. But then to put it into something meaningful, it'll be 0.526 plus or minus 0.01. This is all pounds. This is all in pounds. So what's that going to be? About 0.516 pounds up to about 0.536 pounds. So how do we feel about Del Taco marketing their half-pound bean and cheese burritos as half-pound bean and cheese burritos?
They're generous.
I'm feeling pretty good now on average. Because why? Remember the picture we drew earlier? I'll draw it again here. Half a pound was here. Then we drew a confidence interval based only on our sample data. And as Jared and Michael pointed out, this was just the sample interval. Roughly 75% of our sample was over half a pound. A quarter of it was under half a pound. And we didn't like that very much because we're calling it a half pound. But that was just looking at our sample. As soon as you make an inferential, this is going to shrink down. Now, it has the same center. It's still centered on 0.526 pounds. But now the interval looks different. Now the interval looks like this. This is the actual confidence interval. And what's interesting, I was interested in this. So I looked it up. Can I pull the screen down for momentarily for you guys?
So pound abbreviation isn't actually a British thing, it's a Latin thing?
Oh, it's a Latin thing?
Yeah.
Thank you, I love smartphones. I love me some smartphones.
Is where it came from, and it actually means pound weight.
Where does it come from? What's the word?
Libra pondo.
Libra.
Because in Latin that means pound.
Is that scale?
Yeah.
Okay. That's the symbol, right? Libra? Zodiac symbol.
In the UK, they make sure it's stones.
Stones.
Yeah.
That's like 20 pounds or something.
Something like that, but you're measured.
Interesting. Love me some Google. Check this out, friends. Scroll down here, right here. I was interested. Let's begin at Google. Oops. Here is the nutrition information on a Del Taco half-pound bean and cheese burrito. So I was interested because I said to myself, this is kind of cool. Like how much of the actual, and it comes out 241 grams.
That's a lot of fiber.
It is a lot of fiber. It's also a lot of sodium.
Yeah, it's a lot of saturated.
That's one. Just so you know, it's one. I ate 4 of those at once. Well, not once. Anyway. That's what 241 grams comes out to be on average. So it's 0.53 pounds, which means they're targeting their burrito at more than half a pound. Why do you think they're doing that?
Margin of error.
To account for the margin of error. It's the same reason when you buy a 12-ounce soda, it's not filled on a machine calibrated to 12 ounces. It's usually calibrated to 12.1 or 12.15 ounces. Because there's going to be natural variations in the filling. And this way, even at the low end of the confidence interval, you're still higher than the weight that's being advertised or the volume being advertised. Why? Because we live in America, and somebody will sue somebody for something if it doesn't have that. And what's interesting is, 0.531 pounds, check out. Here's our confidence interval. Notice? It appears to be in our interval. 0.531 pounds appears to be in there. Which means our data, if you will, supports their 0.531. It doesn't refute it. It doesn't refute it. It doesn't prove anything, but it doesn't refute it, I guess, is what the idea is. That makes sense?
Yep.
Paris, go ahead.
Do you think that this argument could be used in a courtroom if someone was actually being sued? Like
It totally could be. And statistics that gets used in courtrooms sometimes gets overturned because it's done poorly. This is done perfectly rigorously, assuming that you can make someone believe our random sample was random enough. The mathematics is, well now, technically speaking, Paris, let's go back to that question. This is wonderful, right friends? You'll never do it manually again. Okay? Not that that was that much work, it wasn't that much work.
Careful, that thing bites.
Sorry. Let's try this again. Okay. Need that bad boy. So Paris, the precision's not enough though. For example, when I put 2 in quotes, it's not 2. It's actually more than 2. And there's a reason for that. Grab your TIs. Let me show you the shortcuts for calculating this interval and then give you the motivation as to why this is called what it's called. Okay, so we're in here. I actually overestimated the standard error right there. I call that 0.005. It's closer to that 0.00456. Go back to your stat menu and go back to tests. Lindsay, you're still in ints over there. You're still in ints. And Paris, yours is going to be called T-int, I believe. Same place you're in for one pin Z. But okay, friends, stat tests. You're not looking for the letter Z anymore. You're now looking for the letter T, which isn't going to make a whole lot of sense at this moment. But you'll see why. The T only has something to do with that number 2 that I put in quotes down there. Everything else is the same as it's always been, but we're no longer going to be using the Z distribution, we're using the T distribution. More on that in a second, So go down to T interval, which is number 8. T interval, which is number 8. Grab him. This input screen looks a lot different. Looks a lot different than the one prop Z int. And it should. You're testing different variables. The first thing it asks you is, where are your input data? Are they actually data or do you have summary statistics? We'll do a little bit of both of these in this class. Right now you have data though. And where is your data? Where did you put it? Right, so make sure your list is on L1. Mine's on L3, so I'll change it. L1. Does your freak say 1? It should say 1, because you're counting all those data points one time. Eventually we'll have distributions. I'm thinking on Tuesday we'll play with distributions in class, but for right now just leave it on 1. Confidence level 95%? Yes, indeed. Calculate. Enter. It thinks a little bit. You'll see why it's thinking a little bit here in about 2 minutes. And look at that. There's our interval. 0.517 pounds up to about 0.535 pounds. Now notice, it's not exactly equal to what we got here. We rounded, we were very cavalier, especially with this 2 that's down here. That's really that's the most, let me show you why I put the 2 in quotes. Okay, sit back and relax. I want to explain to you why this thing is called a T interval. We'll close out class with this. Don't worry about this manual calculation anymore. Everybody follow that T interval. We'll do more of those on Tuesday. I promise you there. Let me show you why this thing is called a T interval. Okay? And then we'll follow this up on Monday as well, or Tuesday. First of all, I want you to read a job description that was posted back in Ireland a few years back. If you would. See if you guys qualify for this job. Well, if I was alive in 1899, I would have. This is, minus the newspaper article, it's a true story. It's a true story. Guinness, when Guinness was basically a microbrew, is responsible for the development of one of the cornerstones of this course, which is amazing. This gentleman right here, William Gossett, was hired in 1899. He is the reason we're talking about this right now. He's the guy that came up with the T in a T interval, okay? Here's the deal. Guinness was a small brewery in 1899. So the large sample sizes that we've already agreed we like to have large sample sizes, he couldn't always get them. Sometimes he had samples of size 4 and 5 and 6. He was testing not only quality control, but also the actual grains that went into the beer manufacturing. We're talking a small operation. So you can't go, I need 1,000 bottles. You can't do that for a number of reasons. Liver is one. But the other reason is you just financially couldn't do that. So his job was to come up with, actually, he needed to come up with this curve, like your Z curve over here. This curve that you mentioned earlier is a Z normal curve. We couldn't necessarily use that over here because the sample size is being too small. So what he did was, he created what's called the student's T distribution. It's a weird story as to why it's called that. He couldn't publish under his own name, so he called it that for some reason. That's the formula for it. Now I showed you the formula for the Z distribution back in 243, and you kind of cringe a little bit then. Did you see how much longer it took the TI to crunch the T than the Z? No, it's not, it's about a second longer, but you can see why. Even for a computer, that is a more interesting, and when I say interesting, more complicated formula than the Z formula. Also, if you look at the formula itself, how often do you see a mu in there? Or an S? You don't see a mu, and you don't see an S. It's only based on the sample size itself. The sample size. T is the variable like Z, sliding back and forth on the scale, so it's the address, if you will. So it's only based on sample size. That formula right there, we're going to come back to this on Tuesday. That formula is the reason that you go to T interval in there. And I got some graphics. We can't really do it well in 5 minutes. We'll do it again on Tuesday when we kind of regroup after go to our homework questions. But this is why it's called a T, because of Guinness. I love that. The fact that the Guinness Brewery has something to do with our class. I think it's very, very interesting. So we'll come back to this. We'll see about why we like the T when we have more than 5 minutes to talk about it. For Tuesday, can you bring questions on estimating a population proportion? I think if you look at your homework sheet, the first one says the mighty central limit theory. We don't need that, obviously, to do the 243. Next one is estimating the population proportion. We'll then get into estimating the population mean, which we're in the middle of doing right now. We'll finish this up on Tuesday as well. Take those home with you. I didn't make them in-class quizzes. Actually, I want you to have them for reference. Is that fair? I have an in-class quiz for you on Tuesday, I promise. Oh, it's called a factorial. Oh, goodness, I just broke something.